AP Chemistry, this is the second part of the answers video for the day 96 assignment on weak acids and common ion effect, okay? So these are the two problems that I did in class on Wednesday, January the 31st. All right, so again, watch these several times. They will start to make sense if you watch them and repeat them. Don't just watch them, but practice them on line paper. So what we're talking about here is a weak acid. It's called formic acid. And we're going to write out the reaction here. So it donates a proton, and you're going to put it in water. So everything is in aqueous solution. That is a water solvent that we're putting this acid in. All right. So there's the arrow. I like to draw that so you don't forget which side is products, reactants. And what's going to happen is this proton is going to jump over onto the water molecule. It's going to be attracted, and that's going to produce a hydronium ion. And that's what defines a solution as acidic. It has hydronium ions in it. And then you're also going to leave the rest of this behind, whatever it left behind. So all that jumped over is the proton, not the entire hydrogen atom with the electron. So that means you're going to leave behind this, and then the electron that hydrogen left behind right there, okay? So this is a weak acid reaction. Okay, formic acid is a weak acid. There's 7 strong acids, and anything that is not one of the strong acids is a weak acid. So what this means is this is sometimes going to happen. This H is going to jump over here sometimes, and most of the time you're going to find it doesn't. So since you're going to be left with some of this in solution and some of this in solution, it's an equilibrium situation. It's a reversible reaction. That proton that jumped over here and made the hydronium, it could jump right back to this. And it could jump right back to this and turn it back into a formic acid. So it's a situation where you still have some reactants left, still have some products, so it's equilibrium. And so this is the equilibrium constant for this particular acid. It's a fixed number at 25 degrees. It's a number you can look up in your book or on Google. What's the acid dissociation constant for formic acid at 25 degrees? And you would come up with this number. All right, so the way we started this problem last time is we have a certain concentration of 1.3 molar, and we're going to start off with the same concentration this time. You don't include water, it's a pure liquid, and you don't start off with any hydronium in the solution. Now this problem, so we're going to go ahead and do this. This is the first of the two problems that are related. So we also start off with no formate ion. So this is formic acid, its conjugate base is the formate ion. Conjugate acid-base pair differ by 1 proton. So when this H jumps off onto the water to make it H3O, it leaves behind this. This is the conjugate base. Why? Because it can accept that proton right back and turn it back into formic acid. So it's a two-way street, and so that's a conjugate acid-base pair. And we're going to learn the significance of those later on in this course, maybe. Okay, so we're going to fill out the Rice table, and what we're trying to find out generally in acid problems like this is what is our concentration of H3O, hydronium ions, because that's going to tell us how acidic the solution is. The more hydronium ions, the more acidic the solution is. Okay, so we do it the same way we did equilibrium Rice tables before. You're going to subtract some unknown change. Since the coefficients in front of everything in an acid reaction is very nice because they're all ones. You almost never, I can't think of any exception to that. So it's going to be minus 1x. I'm just going to write minus x, okay? Coefficient is 1, so there's a 1 in front of the x, minus 1x. And then down here, the equilibrium is simply going to be this, minus the change is going to give you this. So there's the algebraic expression for the reactant. Over here, it's again, the coefficient is 1, so you're going to add an x. Add 1x, and so down here on the equilibrium line you're going to have x, and then over here same thing, you got a coefficient of 1, so you're going to add 1x, and down here you'll have x. So those are the algebraic expressions for this. Now you want to write the law of mass action. Always write it in terms of the equation first. So it's Ka That's called the acid dissociation constant. It is the equilibrium constant for a weak acid reaction. And it's going to equal the products over here, concentrations. The coefficients are 1, so the exponents are going to be 1, so you don't need to write them. Okay, there's products right there. And the reactants over here, you don't include water, it's a pure liquid, so you only include the formic acid. And there it is. Now we're going to come over here and we're going to plug in the algebraic expressions, and I'll go ahead and substitute in the actual number for Ka, so it looks like this. X for that times X for that over 1.3 minus X for the denominator there. Okay, so that's what that looks like. Now what we're going to do is eliminate this X. We're going to use the simplifying assumption. If you assume this number is very small compared to the 1.3, then you can ignore it. You can just use the 1.3 and ignore this little tiny number that's not going to change the 1.3 very much. So I'll come down here and rewrite. And we'll turn this into X squared. And this just becomes 1.3. So now we're going to multiply both sides by 1.3. Cancels and cancels. So I come over here and you have X squared equals 1.3 times 1.8, and that's going to give us 2.34 times 10 to the negative 4th. Don't forget that. Okay, so that means we take the square root of both sides, and so we get X equals the square root of 2.34 times 10 to the minus 4. So go ahead and do that. So it's second X squared 2.34 times 10 caret negative 4, close the parenthesis, and that gives us 0.015. And that's a molarity, it's a concentration. Okay, so what that tells us is that this concentration up here, which is the one of the ones we're interested in for the hydronium, is 0.015. That's what X equals. And so does this one. And this one, if we cared about it, we generally don't, is 1.3 minus 0.015. Then I'm just going to show you what it is. That gives you 1.285. We don't really care about that, but I'm just showing you how you can figure out all of the concentrations, okay? All right, so first question, what is the hydronium ion concentration? That's this right here, and at equilibrium, it's what X was. It's not, okay, don't forget, X is not always the one you're looking for, but it almost always is. So, in fact, I'm going to say 95% of the time. So, hydronium ion is this. That's what defines an acidic solution, determines how acidic, and it equals 0.015 molar. That's a concentration, okay? All right, next, what is the pH of the solution? Go to your acid-base roadmap and find the relationship between the concentration and the pH, and you'll find that it's this. You don't have to know anything about logs, you just have to know how to plug numbers into the calculator and use the log button. So that equals this. And what that's going to give you is negative log, don't have to push the second button, 0.015, close the parenthesis, and that gives you a pH of 1.82. Okay, so that equals the pH. There it is. All right, now let's do it a little smarter this time. If we know the pH, we know there's a simple formula to find the pOH, and that is, so I'm going to skip down to pOH. pOH plus pH equals 14 at 25 degrees. So we know that the pH is 1.82. So if we subtract 14 minus 1.82, and that's going to give us 12.18. So that's the pOH. Okay, so we've got that. We got two of them. All right. Okay, next we're going to go, what is the hydroxide ion concentration? That's the OH. Remember, there's several ways to figure out some of these, okay? So we know that. So if we know the pOH, the hydroxide ion concentration equals 10 to the minus pOH. I think that's easier than using the formula that hydronium times hydroxide equals 10 to the minus 14. That's messy. A lot of scientific notation. I like this a little better. Okay, so it's going to be 10 to the minus 12.18. And you don't have to do these questions in exactly the order I give them to you. Okay. And what's that going to equal? That's going to equal 6.6 times 10 to the minus 13. You got to be careful. It's a concentration, so it's going to be really, really small, okay? Especially in an acid reaction. So 6.6 times 10 to the minus 13. And again, it's a concentration, so it's molar. pHs, you don't have any units of measure, but for concentrations you do, okay? So there's that. So we've got them all. We got hydronium ion concentration, hydroxide ion concentration, pH, and pOH. Okay, use the 5% rule to show that the simplifying assumption is valid. So the 5% rule says what we did was we eliminated this X right here. We just rubbed it out because we said it's really small. So when you finally do get your value of X, which in this case was 0.015, what you do is you say, is that less than 5% of our starting concentration, 1.3? So you make a ratio of 0.015 over 1.3, and then you multiply by 100, and that'll give you what percent of 1.3 that the X value was. So let me write out the general formula. So X over starting concentration of whatever our acid was times 100%. Okay, so let's come over here and do that. So it's 0.015 over 1.3 times 100%. You just multiply it by 100 and then slap a percent sign on at the end. So let's see what that gives us. And that equals 1.15 is what I'm getting. 1.15%. I'm not sure that's what I got in class. Let me just double check that, okay? But it's less than 5%, and it definitely is going to be less than 5%. 0.015 divided by 1.3 equals times 100. Okay, well that's what I got. So 1.15% is less than 5%. So that means the simplifying assumption was valid. All right, and that's how you do that problem. Now we're going to do the same acid, same concentration, but with a common ion, okay? All right, so problem 8. Everything's the same concentration of formic acid, same Ka value. That's fixed for formic acid at 25 degrees. That doesn't change. It's a number you can look up in your textbook or on Google for formic acid. But now we are going to add a basic salt. So it's a common ion. So let's look at what this reaction is with formic acid. It's the same one it was on the last problem. Okay, so when this proton dissociates, jumps to the water molecule, it's going to turn the water molecule into an H3O plus, and then this loses the H, so it's now HCOO, but that hydrogen left its electron behind. It was only the proton that jumped over there, and so it's called the formate ion. Okay, same as the last problem. So we're going to go ahead, and before we put this in, we're going to put this in the water. Okay, we're going to put in 0.5 molar HCOOK. All right, so this is the reaction that's going to form. So we know from our solubility rules that potassium dissociates with anything it's attached to. So that's going to produce this reaction. Plus the potassium ion. So notice that formic acid, the ion produced by formic acid is exactly the same as the ion produced by what's called potassium formate. Okay? Again, we'll talk about basic salts and what that means at a later lesson. But the point is they both have the same ion. They both produce the same ion. That's what the term common ion effect is. Okay? So, how much of this are we putting in? Just to kind of conceptualize it, imagine you're putting this in the solution first. It doesn't matter with reaction. You can put things in any order you want, but just imagine you're putting this in first, okay? So we're going to put in 0.5 molar of this. So when you put in 0.5 molar, just think of it as half a molar, then you're going to end up with 0.5 molar of this and 0.5 molar of this. All right, so what that means is, since this is going to totally dissolve before we even start our formic acid reaction, we're going to take this is what we're interested in, the K is not important, and we're going to stick it here. It's 0.5. So in the last problem, this was a 0. We started off with nothing here. Now we start off with 0.5, the common ion. Now we're going to come over here. We're still using 1.3 molar of the formic acid. We don't do the water, it's a pure liquid, and we're starting off with no hydronium ions to start with, okay? So now go ahead and fill out, pause the video if you need to be sure you know how to fill out this table, all right? So I'm going to subtract x from this side. All the coefficients are 1, so the x's are just x's. Again, this is the same as the last problem. You have 1.3 minus x. Now you're going to add an x here for the hydronium, and you end up with x here. And now you're going to add x here for the formate ion. And now this is where it's different. You're going to end up with 0.5 plus x. All right, so now we have our equilibrium line. Write the law of mass action. It's exactly the same as the last problem, but practice writing it. You want all of this stuff to be second nature, just automatic when you get to the AP exam. And that comes that way by just practicing, writing it over and over and over again. Okay, there it is. Now we're going to plug in our algebraic expressions and our actual Ka value, which is the same as it was on the last problem. Now on the top, I'm going to switch to parentheses. You can do that. I got an x, and now I have 0.5 plus x. I think on the last video, there was a number plus x, and I kept saying minus x. It wasn't a minus x. You could see clearly that it was a plus x. So that was an error on my part. So I'm sure you kind of figured out I was making a mistake when I said minus x there. Okay, so plus x. And then over this. Same thing it was last time. Oops. What am I doing? I gotta get that right. 1.3 minus x. Okay? All right. Now what you can do is this and this you can eliminate. Okay? If they're very small, you're going to assume it's small even compared to 0.5, not just compared to the 1.3, but even compared to 0.5. And it really is. So we're going to just say this is really small, so you can just gently rub them out. They're gone. Now I'm going to come down here and rewrite the equation. Just do a little algebra. And it's going to be 0.5 times x. So I'll just write it that way. 0.5x over 1.3. Okay, so don't let me fake you out on the math. I'll write all the steps out here. I'm going to multiply both sides by 1.3. And they cancel. And I'm going to divide both sides by 0.5. And these two cancel. So all I have left on this side is x. So I'm going to come over here, and I'm going to put the variable over on the left side. I'm just going to switch it around the equal sign. That's legal. That equals 1.3 times 1.8 divided by 0.5. So let's knock that down. 1.3 times 1.8 divided by 0.5. And I get 4.68. Times 10 to the negative fourth. Okay, and that x is the value of our x of our hydronium ion. It is the answer that we're looking for the concentration of hydronium. So it's a molarity. So I'll write it right here. Okay, that's the value of the hydronium ion. So now I can come down here. It says, what's the hydronium ion concentration? That's it. Not because it's the x, but because the hydronium up here says it's the x. Remember, sometimes this could be a 2x or something else, right? Or a 4 minus x. But the case, it's just purely an x, and it almost always is in acid rice table problems. So that means whatever you figured out for this is the answer you're looking for the concentration of hydronium ions. And that's what makes it an acidic solution, is that concentration. And how acidic. So we write that out like this. Hydronium ion molar. Okay, there we go. Okay, again, I urge you to always show your work. I notice I did several steps along the way. I could have done this all on my calculator. I know how to do that. But you want to show your work, because if you make a math mistake and you get the wrong answer, they might give you credit still if all you did was make a math mistake here. If you set this up correctly, all of this, they may give you credit. So you want to always show your work. Plus, if you go back to check the problem an hour later, you know you can follow the steps that you took and check the work. You don't want it, you did it all in the calculator, it's gone. All right, so what's the pH? So pH, go to your acid-base roadmap. It equals the negative log of the hydronium ion concentration. So that's going to be this. Okay, so we'll put that in the calculator. Negative log 4.68 times 10 caret negative 4, close the parenthesis, and I get 3.3. Okay, that's that. All right, now this next easiest thing to do, you've got this one and this one, is I'd go down and do the pOH. So pH plus pOH equals 14. And I'm off screen, sorry about that. There you go. pH plus pOH, so pH is 3.3 plus pOH equals 14. So 14 minus 3.3 is 10.7. Okay, so that's what I get for that. So we have 3 out of the 4 right now. And now the hydroxide ion is going to be, get this off your acid-base roadmap, it's 10 raised to the negative POH, which equals 10 raised to the negative 10.7. And what does that give us? It gives us 1.99, or I'm going to say 2.0 molar. Oh, 2.0 times 10 to the minus 11. Sorry about that. Gotta watch it. There is a negative 11 there. Concentration are always very small numbers. 10 to the minus 11 molar. Okay? Well, I hope that's what I came up with in class. If it's not, we'll work it out. Okay, so you got all 4 of the different parts that you want to figure out. Now the question is, compare the pH of the previous 2 reactions and explain why the second reaction has a lower H3O concentration and a higher pH. So for the reaction we did previously, problem 7, so this is number 7, that was no common ion. We got a pH of 1.82. Remember, the lower the pH, the more acidic the solution. This was for number 7. For number 8, when we had the common ion, we ended up with a pH right here of 3.3. So a higher pH means less acidic. Lower pH is more acidic. So more acidic. And this is less acidic. Okay, so why? So let's go back up here and look at the reaction. When we had no common ion, this side of the room was a 0. That was a 0 in the last problem, number 7. That means it's easier for the reaction to move to the right because this is an uncrowded room over here. It's 0 and 0. So more of this can dissociate and create more hydronium ions. When we then took this potassium acetate and dissolved it in the water first, then we started off, before we even started this acid reaction, we started off with 0.5 molar of the I said acetate, it's formate. Of the formate ion, we started off with that already in the solution. So that, the Chatelier's principle says that this side is more crowded, therefore it's going to tend to favor reactants. Now that doesn't mean it actually moves back to reactants, it just means it favors reactants. It's pushing it back. So that means less of this is going to be able to dissociate and form less hydronium ions, fewer hydronium ions. That means the solution's going to be less acidic. So with the common ion, you have a less acidic solution because you're not able to produce these as easily as if you didn't start off with this side already having some formate ion. So therefore, with the common ion, you end up with a less acidic solution. With no common ion, you end up with a lower pH, a more acidic solution. Okay, so that takes care of this. All the answers that you have or that are on the assignment for the weak acid.